Keeper 3.7, the Alternating Series Estimation Theorem, or ASET. All right, so the first thing we want to talk about is your partial sums. And so again, if you remember, a partial sum is the sum of the series up to a certain term. It's not the entire series, it's not going to infinity, but it's the sum up to a certain term. We can approximate values, or we can approximate the sum of the series using partial sums. But of course, because we're using a partial sum, we're not actually finding the whole sum. Of course, we're going to have a little bit of error in that. In other words, the true sum is going to be off from what we approximate with the partial sum. And so basically, to find your error, you always take your real value, subtract it from or let me rephrase that, you find your real value, and then you find your partial sum value, and you subtract those two, and you take the absolute value of the difference. And so whatever the absolute value of the difference is, that is your error in your partial sum approximation. All right, so again, the alternating series estimation theorem basically says, hey, we can find this error if we know the true value and we can subtract off the partial sum value, we can find out the error. But realistically, if I knew the true value, why would I use an approximation? There would be no reason for me to use an approximation. So the idea with the alternating series estimation theorem, it says basically, since you don't know the true value, you can figure out how off your approximation is or how much error you have by finding the next term. So whatever the next term is, your error is always going to be less than or equal to that value. All right, so the first example says to approximate the sum of the series using the first four terms. And so they're giving us a series, the sum as n equals 1 to infinity of -1 to the n plus 1 times 1 over n factorial. And so the first thing I'm going to do is I'm going to write out the terms of the series. And so I have S of 4 is 1 if I plug in 1. If I plug in 2, I get -1 over 2 factorial. Plug in 3, I get positive 1 over 3 factorial. And then plug in 4, I get -1 over 4 factorial. Now if I work that out, I get 1 minus 1/2 plus the 6 minus 1/24. Add all that together, I get 15 over 24. So I'm saying that I believe the sum equals 15 over 24. And I'm saying that based off the first four terms. Now, of course, I know that's not the actual true sum, but I'm saying it's probably close by some, decimal point away from the true sum. All right, so the next example, we're going to actually figure out how close it is. All right, so part B says use the alternating series error bound to show that this approximation differs from the actual value by less than 1 over 100. So remember, error is simply your remainder. It's the difference of the true value minus the approximated value. And so our true value we'll call S. The approximation that we use on part A was S sub 4. So our error is going to be the difference between the true value and the approximation using 4 terms. Now, using the alternating series error bound, we know that the error has to be less than or equal to the next term. Well, if I use 4 terms for my approximation, then I need to figure out the 5th term to figure out what my error is less than or equal to. In this case, since our function was 1 over n factorial, my error is going to be less than 1 over 5 factorial. Again, using 5 because 5 was the next term after 4. All right, so 1 over 5 factorial is 1 over 120. So I know that my error is less than or equal to 1 over 120. 1 over 120 is less than 1 over 100. So that means the error that or the approximation that I found in part A differs from the actual value by less than 1 over 100. All right, so part C says use your results to show why S cannot equal 0.7. Well, the approximated value that we found was 15 over 24, and the error that we found was 1 over 120. So if I subtract 1 over 120 from 15 over 24 and add 1 over 120 to 15 over 24, I could pretty much figure out a true bound for S. Like I could figure out what S actually has to be between. And so when I do that, I get 74 over 120 is less than S is less than 76 over 120. Or S has to be between 0.616 and 0.633. All right, so Can S be 0.7? Well, the answer would be no, because 0.7 lies outside of those bounds for S. So S has to be a number between 0.616 and 0.633. Since it is not, S cannot be 0.7. All right, last example. It says how many terms are needed to approximate the sum of the series -1 to the n plus 1 over n to the fourth, so that the estimate differs by the actual sum by less than 1 over 1,000. The easiest way to do this is write out your terms of the series. So I'm just going to start writing out sum by plugging in 1, I get 1. Plug in 2, I get 1 over 16. Plug in 3, I get 1 over 81. Notice I don't really care about the negative because the error is the absolute value of the difference, so the negative is relevant. But I plug in all my numbers all the way up until 6, and I see that the sixth one is 1 over 1296. Well, since 1 over 1296 is less than 1 over 1,000, I know for sure that I would have to use 5 terms, because the fifth term, if I'm using 5 terms to make my approximation, I would use the sixth term to get the error. So therefore, I need 5 terms to get an approximation with the sum less than 1 over 1,000.